Just took a little bit of time to go over the homework, and you're taking out your 11.3 notes. As far as the 11.3 notes go, I have in the past done a little activity to get it started, but I think in the end it makes this topic a little more confusing than it necessarily needs to be. So if I have time, we'll come back and do it sort of to enrich your understanding of the content, but preliminarily we are going to skip that little activity and we're going to jump right into our key definition for today. Now, before you go crazy writing the definition, let me be clear. We're going to do two things today in class. The first skill you are going to be able to obtain out of today's lesson, the first thing you're going to be able to do is decide if a data set fits a normal distribution. That's fancy talk for bell curve. Does data fit a bell curve? You're going to be able to answer that question today. After you decide, or if it's decided for you, that data does indeed fit a bell curve, you could start to make predictions about that data. So the second skill you're going to obtain today, you're going to see a couple word problems. You're going to be able to apply your understanding of the bell curve and normal distribution in order to make predictions and solve some authentic word problems, essentially making predictions about real-world data. So here in our definition for today, we have the definition normal distribution. And you see right away, aka it's the bell curve. And we have talked about the bell curve a little bit in class. I'm going to ask you of some real-world examples of the bell curve after we're done with the definition. The bell curve is a symmetric distribution, again, where the mean and the median are equal. But to be honest, you folks know that there's really, so far, two criterion to sort of take a look at before you decide on the shape. So you make a histogram and you look at it. A symmetric histogram is going to make this bell shape. It's going to make this normal distribution. So you use your eyeballs, and if your eyeballs don't do it for you, then you go to your mean and your median. If the mean and the median are the same number, then you have a symmetric distribution, normal curve. And then the next thing, we have this thing called the empirical rule. This will be your third criterion that data should meet. If data is indeed normally distributed, in other words, if you can make a histogram with the data set, and it indeed does make a bell curve or a normal distribution, then all of the data is going to follow the empirical rule. And what that's called is, I also call it the 68, 95, 99.7 rule. If you take nothing else out of today's lesson, you must remember those three numbers. Write them down, memorize them. You could use my husband's approach to memorizing numbers. He always associates it with athletes. I don't know a famous athlete that had a number 68 or 95. I should have probably Googled that before I came in today. But 68, 95, anybody? Okay, so clearly I need to Google that later. I can't think of a 68 or a 95 that was famous off the top of my head. 99.7, I'm like, oh yeah, that's a radio station. So you got two athletes in a radio station. 68, 95, 99.7. Moral of the story, I don't care how you remember those three numbers, you need to remember them. So what do they mean? That takes us to our next slide. Okay, if data is indeed normally distributed, it follows the empirical rule. I have a question for you. Yes, all of you in this room took a quiz yesterday. You made a histogram for me. You did very well. I did not post them in Progress Book yet. I will by the end of the day, but everybody did very, very well. I was very pleased. So congratulations with that. I have a question for you though. The topic was golf scores, right? You had 20 golf scores to make a histogram out of. Out of those 20 golf scores that you took a look at to make your histogram, what percentage of those golf scores got represented ultimately on the histogram? What percentage of them will? 100% of your data values were represented on the histogram. That is true. Any histogram you take a look at is going to represent essentially 100% of your data values. The normal distribution is not different. It's still a histogram. They just smoothed out the edges to make the bell, right? In other words, 100% of your data points will be represented under the curve. The empirical rule, or the 68, 95, 99.7 rule, essentially just breaks this 100% down into chunks. Now, before I go any further, I said I was going to ask you a question a little bit ago. Now I have to go back and ask you that question. Today's topic is the bell curve, or normally distributed data. My question to you is this: what are some real-world examples of data that fits a bell curve? Do you remember? Will, do you remember? Say it one more time. What kind of test scores? Like all test scores? Like, do you think our quizzes from yesterday where everybody got like 9s out of 10s, 10s out of 10s, do you think that that's normally distributed? Am I hearing? Say it one more time. Like, specifically what type? Okay, so she's sort of elaborating on what you're saying, where the average is a C-score. Normal data fits a normal curve, meaning that you have a few high scores and a very high scores, and very few very low scores, but everybody runs towards the average. Typically, IQ tests, if you're talking specifically about exams, IQ exams are normally distributed. Most of us run towards the average. We have very few Mensa members, super intelligent individuals, and then you have very few people who score very low on an IQ exam. So that, if you're talking about exams, that's good. SATs, normally distributed. True story. You have a couple people, National Merit Scholarship qualifiers, high end. A few people really low end. They got points for putting their name on the thing, filling in all those bubbles. But most of us run towards the average on the SATs or ACTs. What else? Perhaps final exams, if we went across, like if we took everybody from Algebra 2 Essentials into our Honors Algebra 2, you could probably say that that's pretty close to maybe fitting a normal curve. Maybe pretty close. We said like average height of adult females, normally distributed. I am the mean and the median. I am 5 feet 4 inches tall. In other words, we have very few very, very tall people. Very few very, very short people. Most of us run around my height. I am average height. So that, what's that? I don't. I think it's like 5'11" in this country, I think. That's also, for, I think it's 5'11". It might be 6 foot even. I don't know. Nobody knows that fun fact? No? Another thing I'll have to Google later. Thanks a lot. Birth weights of babies, we talked about that. That's all normally distributed data. Okay, so more of the story is this. All of that data, 100% of it is on the bell curve, okay? Now, when we go into breaking the bell curve down into intervals, what that empirical rule says is this. 68% of us run in and around the average. If you take a look at it, 68% of us fall within 1 standard deviation of the mean. After that, the standard deviations move outward. So 95% of us get represented within 2 standard deviations of the mean. So you see that after I go through, I keep shading more and more of my bell curve. And then lastly, within 3 standard deviations of the mean, you have 99.7% of our curve. In other words, only 0.15% of us get to hang out on the really high end or really low end of the spectrum. Okay, I'm going to give you a minute because these 2 bell curves are exactly the same. In other words, these 2 graphs are equal to each other. I'm going to give you 1 full precious minute of my class time today. I need you to determine this. Why are these 2 graphs the same? Why is the one on the left the same as the one on the right? 1 full minute. Ready, set, go. Throw the question out to you folks. Why are these 2 graphs the same? Good, Bree. So you start from the inside and work your way out. So essentially what this is saying is that if our mean is here, which it is, x bar is our line of symmetry for our bell curve, that will always be the case. If you break 68% into two equal pieces, you get 34 and 34. So that first interval is still 68% of our data values. One standard deviation above and one standard deviation below. Then, if you break it apart even further, you see that if you put all four of these values together, you get 95%. You could also have worked from your outside in, if you think about it that way. If you would have added 0.15% and 0.15%, you get the 0.3% that's missing to make 99.7, 100%. So you could have also started from the outside and worked your way in, depending on looking at it. Ultimately, if you add every single percentage on the right side here, you get 100%. And we eventually see that this graph on the left is also 100% of our data values. They're the same curve, okay? Sometimes you're probably saying, why are there two, Mrs. Lucas? Why is that even necessary? Sometimes the questions will ask you, what is the percent of data that lies within two standard deviations of the mean? So you have to go 2 standard deviations above and 2 standard deviations below. Sometimes it'll ask you, what range of salaries is 2 standard deviations above the mean? And in which case, you would just look above the mean. So sometimes you need the one on the right, and sometimes you need the one on the left. We're going to discern that in the tail end of our lesson today. So now that we've talked about the normal distribution and the empirical rule, we have to go start doing problems. The first skill you're going to get for today, like I said, is to decide, does data even fit a bell curve? So for that, we're going to go ahead and not look at DVDs, because that's also a little confusing to start with. We're going to look at the light bulb problem. And essentially, this problem runs us through the 3 criterion to check to see if data is normally distributed. The first thing we're going to do, see that line right there? We're going to make a very fast histogram, very fast. So fast we call it a dot plot. Now, it's a way of sort of just plotting each data value and seeing what shape it would make on a line. That's what we're going to do next. So first of all, we need to kind of get some intervals along that line. I need to know the smallest data value out of these 20 100-watt light bulbs. Do you see it, Joshua? What is it? 970. So that's going to be where our number line starts. That's a nice round number, by the way, Joshua. If it weren't a nice round number, I'd probably go a little bit below it. So I usually do like multiples of 10 or multiples of 5 when I do a dot plot. I make the numbers nice and easy to break into intervals. Okay, now I have to look at the maximum lifespan of my 20 100-watt light bulbs. What's the largest data value? Do you see it, Izzy? Yeah, 1,044. I'm going to go a little bit above that. I'm going to go to 1,050, because then I can count by tens. So we have 970, 980, 990, 1,000, 1010, 1020, 1030, 1040, 1050. Now I'm going to start making some dots to plot my data values. Essentially, I make little X's. So for instance, I see 1,013 as my first data value. That's a little bit beyond 1,010, so I'll put an X right there. Not quite halfway, just in between there. 1,000, that's on my number line, so I'll put an X there. 995 is halfway between 990 and 1,000. 1,005 will be halfway between 1,000 and 1010. 1044, almost halfway to 1050. 1,000, notice I'm getting another a repeated data value. That means I put an X on top of the data value I already represented. So if you have, right now I counted two 1,000, so you see I have two X's at that part of my number line, and then I have 1010. 1029 is right before 1030. 1005 is right here. 990. 1000. So I get a third X up there. Do you see that? 1020. 1030. Another 1000. 995. So another one of those. 1010. 982. And 970. So the first thing you're going to do is use your eyeballs and decide, does this graph make a bell? What do you think? Yes, very good. So far I'm leaning towards a symmetric or normal distribution because there is definitely some sort of bell shape to my data. The next thing we have to do is throw this data into our calculator. So criteria number one for the entire chapter so far has been using your eyeballs. If it tails off to the right, it was skewed right. If it tails off to the left, it's skewed left. If it looks like a bell, it's a bell curve. If all the bars were even, it'd be uniform. So those are our four shapes. First step was you used your eyeballs. The second step is you went to your mean and your median to make a decision. And we're also going to need to calculate our standard deviation. When you do your standard deviation, I need you to do SX, okay? Just for this lesson today, okay? Or for this example even. After that, we go back to sigma. So for this example, I want you to use SX, please. So you're throwing this into your calculator right now. You're getting your mean, your median, standard deviation. You're going to write those down. I'm going to continue checking a couple more homework assignments while you guys get those numbers for me. And then, okay. So as I look around the room, you guys are doing a pretty nice job getting your collection. Sorry, my files there. So what we're looking at right now, at least, is this little bit of information. So you folks went ahead and you calculated for me. There's your dot plot. Standard deviation. You should have gotten SX to be 17.2. Your mean, if you were entering it into your calculator correctly, you should have gotten 1,004.15, and then the median is 1,004. Okay, did anybody not get that on their calculator? No? Okay, good job. So you guys are good with the calculator. All right. In the next question, we start to get into some words that we have to translate to some symbols. In other words, we have to write a formula after this. So here the question says, what percent of the data points fall within 2 standard deviations of the mean? Within 2 standard deviations of the mean. That's actually an important phrase. Within 2 standard deviations of the mean. What's up, Calvin? Oh, you did? All right, then. Okay, so thank you, Calvin. Back to this. Within 2 standard deviations of the mean. Let's keep in mind what we're trying to do. We're trying to determine if this data fits a bell curve. So what we're trying to decide is essentially what percent of light bulbs out of the 20 that we got are going to fall within 2 standard deviations of our mean. 2 standard deviations equates to a percent. Can anybody remember from the beginning of the lesson what percent is associated with 2 standard deviations? Ryan, 95%. We want to see if 95% of our light bulbs falls within 2 standard deviations of the mean. If it does, this data is normally distributed. What we have to do is set up some boundaries though. So we get a formula. This within 2 standard deviations of the mean means we have to calculate 2 things. We have to calculate the boundary that's 2 standard deviations above the mean. So you write that as x bar, which you recall is your mean, plus 2 little sigmas, 2 standard deviations. we also have to figure out the lower boundary for 2 standard deviations. Ultimately, we have to count the number of light bulbs that fall within this interval. So the lower boundary that we're going to look for is the mean minus 2 standard deviations. So these two equations are going to give me the number of light bulbs that are, I'm sorry, I won't give you the number. It'll give you the boundaries to count the number of light bulbs within 2 standard deviations of the mean. So I do these calculations. My mean from the previous problem was 1,004.15. And then I'm going to add and subtract not 1 but 2 standard deviations. In other words, 2 17.2s. You don't need to add it on twice. You could just add it by the product of 2 and the standard deviation. Now what this does for us is it sets up an upper boundary and a lower boundary for us to count off. I now need to go back to my set of 20 light bulbs, back to my data, and count how many light bulbs fall within this boundary. How many light bulbs are, between 969.75 hours of life and 1,038.55 hours of life. And you're going to go ahead and do that. Count them up. What'd you get? Brian. Yeah, if you get a 19 out of 20 on a quiz, you get 95%. So look at that. 95% of our data values actually fell within 2 standard deviations above and below the mean. And it's for that reason that our data is officially normally distributed. You see some conflicting evidence up there though, don't you? Look at the mean and the median. What are they supposed to be? The same, right? But ultimately, the data fits the empirical rule. So we used our eyeballs, and it fits the empirical rule, which means it's safe to assume this data is normally distributed. Okay? So that was step 1 kind of done. That would be the process you would have to go through with a data set to decide if it's normally distributed. Next up, we have to do something with this information. I'm going to go back to my other slideshow here. All right, we're going to now make some predictions about some data. We're going to do a couple word problems. So in example 1, we have the salaries of some lieutenant governors from way back. So from 1992 to 1993, the annual salaries of 43 state lieutenant governors in the United States have a normal distribution. In other words, those salaries fit a bell curve, already predetermined. The sample mean is 57,000, and the standard deviation is 22,000. So what they're doing right now is they're giving me some information about my symbols. They're telling me my mean is 57,000, and one standard deviation is $22,000. What I'm supposed to do in part A is determine a range of salaries. Within what range do about 95% of the lieutenant governor's salaries fall? Now, this will be for the entire rest of the chapter, this fun fact. See that 95% right there? You just circled it. Good job. When you see a percent, it equates to a number of standard deviations. When you're given a number of standard deviations, you can translate that back into a percent. So right now I see a percent. Do you see it? 95%. That translates today into a number of standard deviations. How many is it? Well, it is 2 standard deviations. So this equates to plus or minus 2 standard deviations. So what they're saying, to find the range of salaries that fall in that interval, you're going to take your mean and you're going to add on 2 standard deviations, and you're going to take your mean and you're going to subtract 2 standard deviations. So my mean was 57 grand, and we're going to add on 2 $22,000 increments, and then we're going to take $57,000, and we're going to subtract 2 standard deviations. essentially take $57,000 and add on $44,000. The upper boundary is going to be the lieutenant governor that makes, what is that, 57 and 44 is $101,000. Did I get it right? Cool. And then $57,000 minus $44,000. Oh my goodness, that poor guy makes $13,000 a year. Hopefully that's not his full-time gig. Making ends meet on that would be rough. That must be like Rhode Island or something, real small state. $13,000 is what you get. That's social studies. Part B. So about what percent of lieutenant governors have an annual salary between $35,000 and $79,000? So what we have to go ahead and now, see what it's asking me? I'm asked to figure out about what percent. Again, if you're asked or given information about a percent, you have to find a number of standard deviations. If you're given information about standard deviations or asked about standard deviations, chances are you're going to have to look to a percent. It's like a two-way street sort of thing. So here, they gave us the percent. We determined the number of standard deviations. So here they're asking us a percent. I need to figure out, well, what is my standard deviations? So I'm right now, I don't know how many standard deviations above or below the mean I am. But what they do is they give me some information about the boundaries. They give me information that says, hey, you know, the lower boundary is $35,000 and then the upper boundary is $79,000. And I'm looking for the percent of the 43 governors. How many of them, more or less? What percent of those people make that amount of money between $35,000 and $79,000? So to do that, I'm going to go ahead and figure out how that value differs from the mean. In other words, I'm going to figure out the standard deviations associated with those data values. So let's start with 79,000. Ultimately, I'm going to figure out how that differs from the mean. In other words, I'm going to subtract the value of the mean. Difference in math class means subtract. So this tells me how my mean differs from $79,000. In other words, I'm doing $79,000 and I'm subtracting my mean salary of $57,000. Hey, look at that. I get $22,000. Whoops, that's a backwards comma. That is one standard deviation above the mean. And then I need to figure out, well, how is $35,000 different from the mean? And anytime you ask that question, you're determining a number of standard deviations. So I'm going to this time around take my mean, and I'm going to subtract $35,000. So if I do $57,000, and I want to determine how that's different from $35,000, I notice once again I'm off by, hey, $22,000. So that's one standard deviation below the mean. So we've answered our question from the beginning. About what percent, we now know that we are plus or minus one standard deviation, away from the mean. And the number of standard deviations equates to the percent, aka answer. So what percent of data is one standard deviation away from the mean? Eric, 68% of our lieutenant governors will fall within this range. That's very good, Eric. If you needed to figure out exactly how many, what would you do? If it didn't say what percent, if it said how many, what would you do, Izzy? Yeah, you take 0.68 times 43. Work it out. Good job. All right. One last problem. We're going to do part A together. You're going to do B and C. I'm also going to shorten your homework for you in just a moment. All right, so this time around, we get some normalized data. The math scores of the 2004 SAT exam are normally distributed with a mean of 518 and a standard deviation of 114. In part A, it says about what percent of test takers score between 518 and 746. I noticed that 518 is my mean. And now I need to determine how 746 differs from the mean. So if I want to determine how 746 differs from the mean, I'm taking 746 and subtracting the mean. Because differs in math class means subtract. What I notice is that that's 228, which equates to 2 114s, which is the same as 2 standard deviations above the mean. This they actually give to you in that little graph there. What they're asking us is what percent of test takers score between the mean and 2 standard deviations above. So 518 and this data value is 2 standard deviations above. In other words, I need to figure out what percent of data is in that part of my curve. Do you know, Will? What is it? How did you get 47.5? You're absolutely right. You could do that. Yes, that's great. I wasn't thinking that way. Yeah, take 95, cut it in half. Perfect. Most of my students, just from my period 1 class and like the rest of my career, they were taking 34 and adding on the 13.5 from the other chart. But if you take 95 and just cut it in half, that's great too. Perfect. Any way you slice it, well, it is 47.5. No pun intended. Remember, you don't write it down if you don't understand it. Do you understand where 47.5 came from? Calvin. Okay, was that going to be your question? Okay, so, well, where did you get 47.5? Where did you get the 95? That's a good question, too. When you see a standard deviation, Calvin, like I've been saying during today's lesson, when you see a standard deviation, that equates to a percent, and vice versa. 2 standard deviations, you're thinking in the back of your head 95%. But we only want it above this time. We only want it above this time. Your assignment, I did say it was going to be shorter. This will be on Blackboard too if you got to skedaddle, but oh, come on. I just lopped off 3 through 8. 3 through 8, you're not doing on your assignment tonight. It's the same assignment. I'm just taking away 3 through 8. You'll know it because the notation in them, you're like, what is that? You could probably do the problem, but the way they question you is weird. So that is your official assignment for tonight. Have a nice evening.